A shift has taken place in one of the most remote regions on Earth, and its implications extend far beyond the frozen edges of Antarctica. For decades, a quiet anomaly puzzled scientists and resisted easy explanation. Why did Antarctic sea ice expand while much of the rest of the planet warmed? What hidden forces allowed this icy shield to grow even as global temperatures climbed? And more importantly, what changed so abruptly that this long-standing pattern reversed in a matter of months? The answers now emerging point to something far more significant than a simple fluctuation. Evidence suggests that a threshold may have been crossed, one that alters how the Southern Ocean behaves and how the planet regulates heat. The scale, speed, and persistence of this change raise urgent questions about whether the system can return to its previous state or whether it has entered an entirely new phase. Since the late 1970s, satellites have provided continuous observations of Earth's polar regions. These records revealed a striking contrast between the Arctic and Antarctic. In the north, sea ice declined steadily, matching expectations in a warming world. In the south, however, sea ice showed a gradual expansion. Year after year, the frozen perimeter surrounding Antarctica pushed outward, confounding predictions and forcing scientists to reconsider how regional processes could temporarily counter global trends. This expansion was not dramatic in any single year, but over time it became unmistakable. By the mid-2010s, Antarctic sea ice reached its largest recorded extent. At its peak, it covered millions of square kilometers, stretching across vast portions of the Southern Ocean. In square miles, this equated to an immense frozen area that rivaled entire continents. The persistence of this growth suggested that unique oceanic and atmospheric conditions were at work, maintaining a delicate balance that allowed ice to form and survive. Then, around the year 2015, that balance broke. Within just a few months, Antarctic sea ice experienced a collapse so rapid that it stood out as one of the most extreme events ever recorded in the satellite era. The total loss ranged between an area roughly equivalent to 1 to 2 Greenland-sized regions. In kilometers, this represented a reduction of millions of square kilometers. In miles, the loss spanned vast stretches of ocean that had previously remained frozen even during seasonal transitions. The statistical nature of this event drew immediate attention. In climate science, variability is expected, but there are limits to how far systems typically deviate from their average behavior. This collapse reached deviations measured at up to 7 standard deviations from the mean, a level so rare that it falls far outside what would normally be considered natural variability. Events of this magnitude are often described as extremely low probability occurrences, yet this one unfolded in real time, captured by satellites orbiting hundreds of kilometers above the Earth. The abruptness of the shift was only part of the concern. What followed proved equally troubling. Instead of rebounding to previous levels, Antarctic sea ice remained consistently below its historical average. While there were brief periods of partial recovery, these were short-lived and insufficient to restore the earlier trend. Another major decline around the early 2020s reinforced the emerging pattern, suggesting that the system had not simply fluctuated, but had fundamentally changed. Understanding why Antarctic sea ice had expanded in the first place became critical to interpreting this reversal. One key mechanism lies in the formation of dense bottom water in the Southern Ocean. When seawater freezes, it expels salt into the surrounding liquid. This process creates extremely cold, salty water that becomes dense enough to sink toward the ocean floor. As it descends, it helps drive a global network of currents that circulate heat, oxygen, and nutrients throughout the world's oceans. This circulation is not a minor component of the climate system. It acts as a conveyor, redistributing energy across vast distances. The sinking of cold, dense water near Antarctica plays a central role in maintaining this movement, linking the polar regions to the deep ocean basins that span thousands of kilometers and miles. Sea ice contributes to this process while also performing additional functions that influence the global climate. One of the most important is its ability to reflect sunlight. The bright surface of ice sends a significant portion of incoming solar radiation back into space, reducing the amount of heat absorbed by the planet. In contrast, open ocean water, darker in color, absorbs more energy and warms more rapidly. This difference creates a feedback loop. Less ice leads to more absorption, which leads to further warming and additional ice loss. Sea ice also serves as a protective barrier. It dampens the force of ocean waves, shielding the edges of Antarctica's ice shelves. These floating extensions of the ice sheet act as buffers that slow the movement of land-based ice into the ocean. Without the stabilizing presence of sea ice, wave energy can reach these shelves more directly, increasing the rate at which they fracture and erode. Despite rising global temperatures, the Southern Ocean maintained a structure that supported sea ice growth for decades. The upper layer of the ocean remained relatively cold and fresh, while warmer, saltier water stayed trapped below. This layering, known as stratification, prevented heat from rising to the surface. Strong westerly winds further reinforced this arrangement by pushing surface waters outward, allowing colder water to remain near the ice-forming regions. Over time, however, this structure became increasingly unstable. Gradual warming of deeper ocean layers introduced more heat into the system. At the same time, shifts in wind patterns altered how water masses moved and mixed. These changes weakened the separation between the cold surface layer and the warmer water below. Around the mid-2010s, the barrier that had kept heat contained began to break down. Warmer, saltier water started to rise toward the surface, disrupting the conditions necessary for ice formation. As this mixing intensified, it reduced the extent and thickness of sea ice, exposing more open water to the atmosphere. This marked the beginning of a self-reinforcing cycle. With less ice to reflect sunlight, the ocean absorbed more heat. As temperatures rose, further ice formation became more difficult, leading to additional losses. Each step amplified the next, pushing the system further away from its previous state. By the early 2020s, the cumulative effect of these changes became undeniable. Antarctic sea ice reached some of its lowest recorded levels, again deviating sharply from historical norms. The persistence of these low levels suggested that the ocean had retained enough heat to prevent a return to earlier conditions. The implications of this shift extend beyond the immediate loss of ice. The Southern Ocean plays a crucial role in regulating global climate, and changes in its behavior can influence systems far from Antarctica. One such system is the large-scale circulation that transports heat through the Atlantic Ocean. A slowdown in this circulation could alter weather patterns across multiple continents, affecting everything from temperature distribution to precipitation. The ecological consequences have already begun to emerge. Species that depend on stable sea ice conditions face increasing challenges as their habitats become less predictable. In some regions, ice has broken apart earlier than expected, disrupting breeding cycles and reducing survival rates. These localized impacts reflect a broader trend in which environmental stability is being replaced by rapid and unpredictable change. Measurements indicate that parts of the Antarctic system may be approaching thresholds beyond which recovery becomes increasingly difficult. The ocean's ability to store heat means that even temporary disruptions can have long-lasting effects. Once additional heat is absorbed, it can remain trapped for extended periods, continuing to influence conditions at the surface. The scale of the recent changes has prompted a re-evaluation of how Antarctic processes are represented in climate projections. Some models may not fully account for the speed at which such transitions can occur, raising the possibility that future estimates of sea level rise and global temperature increase could be conservative. At the same time, the underlying drivers of this shift continue to evolve. Atmospheric conditions, ocean temperatures, and wind patterns interact in complex ways, creating a system that is highly sensitive to change. The interplay between these factors determines whether the current state will persist, intensify, or stabilize at a new equilibrium. As observations continue to accumulate, one reality becomes increasingly clear. The Antarctic system is no longer behaving as it did in previous decades. The processes that once supported expanding sea ice have been disrupted, and the consequences of that disruption are unfolding across multiple scales, from microscopic ocean interactions to global climate dynamics. The central question now is not limited to what has already happened, but what comes next. The trajectory of change unfolding around Antarctica is no longer defined by isolated anomalies, but by a sequence of reinforcing shifts that point toward a sustained transformation. What was once considered a regional irregularity is now being interpreted as part of a broader reorganization of the Southern Ocean system, one that carries measurable consequences for global processes that depend on stability at the poles. As sea ice coverage declines and remains below long-term averages, the immediate effect is a growing exposure of the ocean's surface. This change alters the balance between heat entering and leaving the planet. With less reflective ice, more solar radiation is absorbed directly into the water. Over time, this additional energy does not simply disappear. It becomes stored within the ocean, particularly in its upper layers, where it can influence atmospheric conditions and feedback into the system that governs ice formation. This accumulation of heat introduces a lag effect. Even if external conditions stabilize, the stored warmth within the ocean continues to act on the surface, delaying or preventing recovery of sea ice. In practical terms, this means that the system carries a memory of past warming events, making each subsequent season more vulnerable to reduced ice formation. The longer this pattern persists, the more difficult it becomes to reverse. At the same time, the structural role of sea ice in protecting Antarctic ice shelves is weakening. Ice shelves extend outward from the continent, floating on the ocean while remaining attached to land-based ice behind them. Their stability is influenced not only by temperature but also by mechanical forces. When sea ice is present, it dampens incoming wave energy, reducing stress on these floating platforms. Without this protective layer, waves travel across open water and strike the ice shelves with greater intensity, over distances that span hundreds of kilometers and miles. This increased wave action can contribute to fracturing along existing weak points within the ice. Once fractures expand, sections of ice shelves can break away in large pieces. These events do not directly raise sea levels, since the ice is already floating, but they remove a critical barrier that slows the flow of grounded ice from the interior of the continent into the ocean. When this inland ice begins to accelerate, the consequences become global. The Antarctic ice sheet contains vast quantities of frozen water, and even a small increase in the rate at which it enters the ocean can translate into measurable sea level rise. Current projections already account for ongoing melting, but the recent changes suggest that these projections may underestimate how quickly certain thresholds can be approached. One of the most significant concerns involves the interaction between Antarctic processes and global ocean circulation. The formation of dense bottom water near the continent acts as a driver for deep ocean currents. As conditions change, the rate at which this dense water forms can be affected. A reduction in this process has the potential to alter circulation patterns that extend across entire ocean basins. Among these is the system responsible for transporting heat through the Atlantic. Although geographically distant, it is connected through the global network of currents. A slowdown in this circulation, even by a fraction, can shift temperature gradients that influence weather patterns across regions spanning thousands of kilometers and miles. Changes in rainfall distribution, storm intensity, and seasonal variability can all be linked to disruptions in this interconnected system. Estimates indicate that under continued warming, major circulation components could weaken by as much as 40% by the middle of the century. Such a reduction would not occur uniformly, but would unfold over time, with incremental changes compounding into larger shifts. The Antarctic contribution to this process lies in its ability to regulate the production of cold, dense water that feeds into the deeper layers of the ocean. The persistence of low sea ice levels also has implications for ecosystems that have evolved under relatively stable conditions. In regions where ice once formed consistently each year, its absence or early breakup disrupts established biological cycles. Species that depend on ice as a platform for breeding, feeding, or protection are forced to adapt to conditions that change more rapidly than before. In certain documented instances, large breeding colonies have experienced significant losses when ice broke apart before young individuals were ready to survive in open water. The scale of these losses highlights the sensitivity of polar ecosystems to even small shifts in timing. When such events occur repeatedly, recovery becomes increasingly difficult, leading to long-term population declines. Beyond ecological impacts, the physical changes in Antarctica are influencing how climate models interpret future scenarios. Traditional models rely on historical data to simulate how systems respond to external forcing. However, when a system undergoes a structural shift, past behavior may no longer serve as a reliable guide. This introduces uncertainty into projections, particularly when estimating the pace of change. Recent observations suggest that once extreme reductions in sea ice occur, the likelihood of returning to previous levels diminishes. This is partly due to the feedback mechanisms that reinforce the new state. The ocean absorbs additional heat, the atmosphere responds to altered temperature gradients, and the cycle continues. Each component interacts with the others, creating a network of influences that stabilize the system in its altered condition. The concept of a tipping point is often associated with irreversible change, but in practical terms, it represents a threshold beyond which recovery becomes increasingly unlikely within meaningful timeframes. In the case of Antarctica, the concern is that the combination of ocean warming, altered wind patterns, and reduced ice cover has pushed the system past such a threshold. If this interpretation is accurate, the long-term outlook involves a southern ocean that remains warmer and less ice-covered for extended periods. The consequences would extend across multiple domains, from sea level rise to global heat distribution. The duration of these effects would not be measured in years or decades alone, but could persist for centuries, given the slow dynamics of deep ocean processes. Despite the scale of these changes, the rate at which they unfold is still influenced by external factors, particularly the amount of heat entering the system. Reductions in global emissions can slow the accumulation of energy within the ocean, limiting the intensity of feedback loops. While this does not guarantee a return to previous conditions, it can moderate the pace of change, providing more time for adaptation. Continued monitoring remains essential for understanding how these processes evolve. Satellite observations combined with measurements taken directly in the ocean provide critical data that helps refine models and improve projections. As more information becomes available, the picture of Antarctica transformation becomes clearer, revealing both the mechanisms driving change and the potential pathways forward. At present, the evidence points toward a system that has shifted into a new mode of behavior. The expansion of sea ice that once defined the region has given way to a pattern of decline and variability that aligns more closely with broader global warming trends. The difference lies in the speed and scale at which this transition occurred, marking it as a significant event in the context of Earth's climate system. The broader implication is that changes in remote regions can propagate through interconnected systems, influencing conditions far beyond their point of origin. Antarctica, once perceived as isolated, is now understood to be deeply integrated into the mechanisms that regulate the planet climate. As this transformation continues to unfold, the importance of understanding its dynamics becomes increasingly urgent. Each new observation adds to a growing body of evidence that the stability of polar systems cannot be taken for granted. Instead, they must be recognized as active components of a changing climate, capable of shifting in ways that reshape global conditions. If you found this breakdown clear and informative, make sure to like, share, and subscribe for more in-depth updates like this. And do not forget to tap that hype icon to help this reach a wider audience and keep more people informed about the changes shaping our world.